Welcome to this lecture series in linear algebra. In this lecture, we'll learn about quotient spaces and an associated theorem, or rather, multiple associated theorems. Let us recall what we need. So we need to know about cosets. If we have a subspace U of a vector space V, then cosets of the subspace U are defined as the sets of these form, right? So these are cosets. We talked about this in detail. Then we need to know about how to export set theoretic quotienting. This stands for set theoretic quotienting to the setting of linear algebra. What we did was we saw that if we have a linear map from a vector space V to a vector space W, then just by set theoretic quotienting, this factors through the set of all the cosets of the kernel, because the set of all the cosets of the kernel of T are precisely or is precisely the set of all the non-empty fibers of T, and hence T factors through this set. And we saw that there is a unique vector space structure here which makes both pi and T bar linear. In fact, there's a unique vector space structure here which makes pi linear, and that automatically makes T bar linear. So this linear map can be thought of as a composition of two other linear maps, and that is what we saw in this lecture about exportation of set theoretic quotienting to linear algebra. Then we need to know about how to extend, or the fact that any linearly independent list in a vector space can be extended to a basis. This is very, very basic. We discussed this way earlier. And lastly, we need to know about if we have a linear isomorphism, then the dimensions of the domain and the target space are the same. All right, so let us continue. Here are some problems for practice. And now let us get started. So we will be discussing first the notion of quotient spaces. Fix a vector space V and let U be a subspace of V. The question we are asking is, can we define a quote-unquote natural vector space structure on the set of all the cosets of U? So what do we mean by natural? By natural we mean, or that is there a vector space structure on V mod U which makes pi, the natural projection map, linear, right? So in our lecture on exporting set theoretic quotienting to linear algebra, we saw that there is a unique vector space structure on the kernel of a linear map with V as its domain, such that this guy is linear. We are just asking that question in a context where there is no linear map. All we have is a vector space V and its subspace. Can we have a vector space structure here which makes this guy linear? And the answer is yes. And basically the argument or the proof is pretty much the same as we saw in our discussion on exporting set theoretic quotienting. So let me just sketch out what I'm trying to do. So first, notationally, we will replace this with that, V bar, okay, and define addition and scaling on V bar as follows. So the addition is defined as, we have two cosets, we add them representative wise, and scaling, here F is the base field, scaling is defined also representative wise. Okay, and check well definedness. Check well definedness and also check that, and let me decorate this with colons so that it is clear that we are defining it. Okay, so check that is a vector space over F. Okay, so this is verbatim the same as what we did in our lecture on exporting set theoretic quotienting. Okay, so there is a natural vector space structure here on the set of all the cosets of V mod U, and this is called the quotient space obtained using U. All right, but I want to talk about a pictorial way of understanding it. So suppose we have a subspace U of R2, we will use R2 to foster our understanding. Unfortunately, yeah. So this is a subspace, capital U. Then what are the cosets? The cosets are all the lines parallel to U. So let's say this is a coset, and this is another coset. Now we want to see how to add these two cosets. I need a little bit more space, but perhaps this should suffice. So let's see how to add these two cosets, meaning this one and that one. They are elements of this vector space V mod U. We just want to geometrically see what is the sum of these two cosets. So pick two representatives. What are the representatives of this coset? All the points of this coset. They are precisely the representatives. So pick a representative. This is a representative, this point, and let's say we choose a representative for that. So the recipe for addition is, once you have chosen representatives, just add the representatives as you do in the parent space, and then take the corresponding coset. So we add these two things using parallelogram law. Okay, we added them. We obtained this vector, and the corresponding coset would be that line. So just so that we do not intrude upon the written text, let me translate everything. Okay, so this is how we add things representative wise. First you choose representative, then you add them, and then you take the coset. The question is it sensitive to the choice of representatives? It is not, because you can experiment. Instead of this one, suppose we had chosen this representative, you would find that the sum of this guy and that guy would again lie on the same coset, and hence it is well defined. So this is the geometric meaning of this addition. Similarly, you can think about the geometric meaning of that. It is much simpler, in fact. Okay, so that is the definition of quotient space. Given a subspace, you can always form a quotient space. So that's a very nice example of new vector spaces arising out of old. Okay, so now we have defined quotient spaces. Natural question arises, if U is a subspace of V, and of course we are always working with finite dimensional vector spaces, so V is already assumed to be finite dimensional. Question is, what is the dimension of this guy? What is the dimension of the corresponding quotient? And the answer is very simple. It is just the difference of the dimensions of the two spaces. Okay, and the proof is also very simple. The proof is, just pick a basis for U. Okay, we have a basis for the subspace, and by the extension theorem that we recalled in the beginning, we can extend this to a basis of V, because after all, these are in particular linearly independent. So we can find vectors V1 up to Vk such that the appended list is a basis for the parent space. Okay, the point is, we claim that this forms a basis of the quotient space. Okay, which we will denote as V bar, of course. And just to remind, V1 bar is the coset of V1, and so on. So we need to check two things. First, we need to check that this is a linearly independent list, and second, we need to check that this is a spanning list. So for linear independence, say we have a linear combination that vanishes. This is 0 for some scalars alpha 1 up to alpha k. We want to show that each alpha I is 0. Want to show that. So it's straightforward. We have, by definition of addition and scaling in the quotient space, we have that this is 0. Why? Because this is exactly that. Okay, so that thing is 0, and hence, by definition of the quotient space, this guy lies in the subspace. So this 0 was representing the 0 of the quotient space, and therefore this lies in U, which implies alpha 1 v1 plus dot 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 can be written as a linear combination of ui's. But now you use the fact that v1 up to vk along with u1 up to um are linearly independent, and hence each alpha I and each beta j must be 0. Okay, so just be mindful of that argument. So this implies each alpha I is 0, and we have established linear independence. Okay, now for the spanning part, maybe I'll just do it here itself. No need to go to a separate page. So to check spanning property, let some vector be arbitrarily chosen, and we want to show that this coset is in span of v1 up to vk bar, v1 bar up to vk bar. That is what it means to show a spanning property. All right. So first, since this is a basis for the vector space V, we can write little v as a linear combination of those guys. So we have, I'm not writing that line, so we have the vector space V is for some scalars alpha 1 up to alpha k and beta 1 up to beta m. Just take cosets on both sides. So we get v bar is equal to plus the coset of that, but this already lies in the subspace U, and hence the coset of it is 0, so there is no need to write anything. And now, what is this guy? This guy is nothing but this guy by definition of addition and scaling in the quotient space, and therefore we have expressed v bar as a linear combination of v1 bar up to vk bar, and that establishes the spanning property. And this finishes the proof of the fact that this is a basis for this quotient space. And now it is clear that the dimension of the quotient is the difference of the dimensions, because the dimension of the total space is k plus m, the dimension of the subspace is m, and therefore the dimension of the quotient spaces, which is k, is same as the correct thing, the difference between m plus k and m, which is k. All right, so we now know how to find out the dimension of the quotient of two spaces, meaning quotient of a vector space by its subspace. It's just the difference. And this leads us to a very important theorem called the first isomorphism theorem. Fix a linear map. Then by set theoretic quotienting, or by what we saw when we exported set theoretic quotienting to linear algebra, we saw that we have this diagram. And this is injective. This is the natural projection map. The vector space structure here is same as the quotient space structure. Just think of it as a subspace, and we have the quotient space structure. This is an injective linear map, and therefore we have this isomorphism. T bar is a map from this, and we can restrict the image to the image of T bar. This is an isomorphism. Again, why is it a linear isomorphism? This is an injective linear map, so it is a linear isomorphism from the domain to the image. That's all that we have written. But what is the image of T bar? The image of T bar is same as the image of T. After all, T factors through this thing to give you T bar, and hence T and T bar have the same image. Just verify that if that is not immediately clear. Image T is equal to image T bar, and therefore we can remove the bar here. And now, since T bar is a linear isomorphism, we get that the dimension of these two things are equal. But anyway, the first isomorphism theorem is just this much, that T factors injectively through the quotient space coming from the kernel to give a map T bar between this and that. This is the first isomorphism theorem, and just realize that this is a linear isomorphism, which is where the name isomorphism comes in this theorem. All right. So an immediate consequence of this is the rank-nullity theorem. We have any linear map, then dimension of kernel of T plus the dimension of the image of T is the dimension of the domain. The proof is just use the first isomorphism theorem. By the first isomorphism theorem, we have an isomorphism T bar from the previous page. This is an isomorphism. Therefore, we have dimension of this quotient is dimension of the image, because isomorphisms preserve dimension, as we recalled. And we know that the dimension of the quotient space is this. And now just shuffle things around to get the desired equality. Okay, so that is the proof of the rank-nullity theorem. This is called the rank-nullity theorem. This thing is called the nullity of T, this number, nullity of T, and this is called the rank of T, which is why this is called the rank-nullity theorem. All right, so this is a very important theorem, and we will be using it throughout the course over and over again. And the same for the first isomorphism theorem. Actually, the first isomorphism theorem is at the heart of this statement. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.